Okay, welcome to this first set of lectures. Basically, on data analysis using clustering, classification, regression. A lot of the things we're going to learn, and a lot of the tools, mathematical tools here, sort of form the basis of what you might call data mining or machine learning. And so part of what we want to address is what are some principled ways to think about data, and how do you go about taking data in, looking for patterns in your data so that you can do a variety of things. Not only do you want to do things like classification tasks, where you identify a new piece of data and you classify it as something that you know. You may also want to do some kind of looking for clusters in your data. Maybe you don't know much about the data and you want to just try to understand, are there patterns of the data which you don't know about and you're trying to discover. And there's also ideas of regression, which are, can I actually take my data, think about doing curve fitting to that data so that I can make predictions based upon that data and apply it to new data. Okay, so we're going to talk about some of the key ideas. And some of the key ideas revolve around this idea of learning from your data. So we might think about this as generically learning, or you might want to just call it data mining. And the idea is to think about taking that data, looking for structure in the data, and it comes in two broad techniques. And I'm going to go through both of them here now, which are, and in fact, in the series of lectures, what we're going to do is cover a lot of the key technologies, a lot of the key methodologies around these methods. So the first thing I'd like to highlight is this idea of unsupervised learning. So the idea here is, just as it sounds, is that you're going to basically generate an algorithm on your computer that's going to look for patterns in the data. You're not going to label any of the data. You're going to tell the computer what kind of data it is. The goal of the algorithm itself is to discover these patterns in the data without you being the architect of that discovery process. Another type of data analysis is called supervised. Supervised learning is a little different. This maybe assumes that you know something of your data, and then the idea would be is to capitalize on what you know, and perhaps you even can classify some of your data. You might think about pictures of dogs, pictures of cats. And if you have cats and dog pictures, how would you take these dog and cat pictures and let's say maybe I have 100 dog pictures and 100 cat pictures. I'd like to do a training algorithm so that if I give you a new picture of a dog or cat, your computer could actually classify that as a dog or a cat. And that's the idea of supervised learning, is that you're going to label data ahead of time in this process so that you can make future decisions based upon that learning process. Now, interestingly enough, these two algorithms are trying to do different things. In unsupervised learning, the goal of this is to look for patterns. The goal of this is to take your data and discover clustering in the data in some kind of space. Okay, so unsupervised learning is really about, patterns in your data, or looking for clusters in your data. And we'll show some examples in a little bit with this. So this is this data mining operation. You don't know anything, you're just going to put it in there, go look for things, and hope that, in fact, that you can do a good job in finding those things. Supervised learning is different, because in some sense it's already assuming that you might have clusters. The cat-dog example is one where you say, I have pictures of cats, pictures of dogs, and so I already have clusters. I already know that I have dogs. I already know that I have cats. So you are the expert in the loop. And in this idea, you are providing labels. So you're going to label the data ahead of time, And you're going to give this data some, okay, I have dogs, I have cats, I labeled them all, I know what they are. And now the idea is to make use of that. And if I give you a new dog or a new cat, can you actually label it correctly yourself? Or how can I write an algorithm to do that? Okay? So this is going to involve the idea of providing labels for data, and then you're going to try to see what you can do with new data. How do I label new data? And so there's going to be this training phase, and then a test phase. So the training algorithm, the idea behind the training is to sort of take these ideas, use the fact that you know what cats and dogs are, so you can train an algorithm to recognize what the key structures of the data are based upon your expert-in-the-loop opinion, and then you can go test new data and see how well you did. Okay? So to one idea then is clustering is happening here in the unsupervised learning. You're looking for clusters. You're looking for patterns in the data. In contrast, here in the supervised learning, you're not necessarily looking for clusters. You've already told it by providing the labels what the clusters are. So what you're kind of trying to do in this case here is actually do classification and also regress. So the idea behind classification and regression is if I can do classification, I can find some kind of regression curve or some kind of basically a best least square fit type curve to the data. It doesn't have to be linear. That actually explains this classification data. So that's kind of the big picture thinking behind these two learning algorithms. And we're going to hit a lot of the common algorithms used for both. Now, before we get to that, though, what are the advantages and disadvantages? Well, in unsupervised learning, the disadvantage is that you don't give any information or expert information or knowledge to your algorithm. So it has to figure it out all by itself. It may not even know the right number of clusters. Suppose, for instance, you have dogs and cats. In an unsupervised algorithm, the data is not going to, if you're just letting this thing look for patterns in the data, it may not know that I'm looking for two distinct clusters, dogs and cats. Okay, so that can be a drawback here, and it's actually typically the Achilles heel of this methodology. And this is why you want supervised learning, because here you're kind of telling it what to look for ahead of time, or you'd like to, but the unsupervised learning doesn't have that capability unless you enforce it yourself. Okay? The supervised learning, on the other hand, already assumes the kind of things that you're looking for, which is you're going to give it a training set, and you're going to provide labels. So maybe you already have two data types, dogs, cats. And so it already knows. It doesn't have to look for how many clusters am I looking for the data. It already has that information, and you gave it to it. Okay? And not only that, you gave it expert opinion to start building a training set off of this thing here. And so there's some kind of advantages with supervised learning. But the disadvantage of supervised learning, of course, is that there's a long time training stage sometimes. So you take a lot of data, and if you want good classifiers, oftentimes you have to go through a long time training stage, in other words, to do the classification. Okay, so let me show you an example of what this might look like. So, and then we're going to program in MATLAB. Okay, and I'm going to do this here. I'm going to show you what this might look like. Let me come over here and pop some data out for you here. Okay, so for instance, this could be some kind of data set where I'm looking at, in some abstract representation, here's a bunch of green squares. And they could be, let's say, dogs or cats or some kind of projection of dogs and cats into a two-dimensional space, right? So it's kind of nice. They kind of are here and clustered, and each dot would represent a different dog, for instance. So that's kind of a sampling of data that you might have. And then you could also have a different type of data. And let's represent this in orange. Sure, that sounds great. And suppose those are your data sets. So now what you see is you have these two data types. You have the green, you have the orange. And of course here, it's almost trivial to say that they're different, right? Here you can say, well, there's the green and the orange. I see clearly the difference. And the idea then would be to say, oh, what I will do is form a cluster around the green and a cluster around the orange. Okay? So that's one operation that you might start to think about doing, is that you can easily do this classification task. Now let's talk about how it relates over here to the unsupervised and the supervised learning. If you're in an unsupervised learning algorithm, then you don't even know that there's two things, two objects, let's say green and orange dots. So ahead of time, you're going to have to make some decision. You're going to say, hey, I'll train my algorithm and say, go look for two clusters, for instance. And in that case, if you pick two, and clearly there are two, what it would do is start to figure out, can I form two clusters? And the idea would be, here's a cluster 1, and here's a cluster 2. Okay? Now, the unsupervised learning, that's all it essentially does, is it provides a way, a principled way, to do that clustering. Now, what's interesting is you can use the unsupervised learning and then feed it into the supervised learning. Because once you have the clusters, it's equivalent to providing labels. Now, the supervised learning, what it tries to do is to say, well, I have this data. I've given expert in the loop opinions. And for instance, I could say, hey, these are green squares. These are orange dots. I've labeled them so you know what they are. So you already know there's two clusters, two types of data. And so the idea is, what happens if I have new data in the system? So for instance, let's take a look at something like this. Suppose I have a new piece of data right there. And the question comes, so this is something where I've already got my clustering, so now I want to go down to my supervised learning algorithm, which is to say, what is this? If I give you a new piece of data and it sits right here, what is it? And of course, from the naked eye, you would say, well, I don't know, it's up here with all the greens. It's probably a green. So that's how that supervised learning would do. It would go right down to this classification and regression. And in fact, you might even say what classification and regression are really going to try to do for you here in providing a training is to sort of decide how to separate this data. So for instance, you might separate the data like this. Anything above here is green. Anything below there are orange dots. So this example is very simple. So even if I do classification of that orange circle, or this circle here, it's clearly above here with the greens. I would classify it as a green square. And if I had something down here, a piece of data down here, let's say this X, and I say, what is that X? Well, I'd say, oh, look, it's actually sitting down there with the cluster of orange balls. So I would label it as an orange ball. Okay? So that's the idea here, is that you have a training set, let's say the green and orange, and now your test set are these new data points. So if I gave, for instance, if this was dogs and this was cats, if I gave you this new point, I'd say, oh, that's a cat. I think I said that was, let's say that's a cat. Let's make this up. Let's say these are cats down here. Let's say, and these are dogs up here. Okay? So then any dots down here would be cats. Any dots up here, cats down here, dogs up here, and that's the simple classification. Okay? And again, you can get at these through these different type of methodologies. In this case, if you knew it was dogs and cats, you would say, oh, look, I can already know that there's two sort of types of data in there, so I'm going to go ahead and classify it as such. Okay? So this is kind of the general idea. And again, unsupervised, this is a really key concept. Unsupervised, essentially, for data that you don't know anything about, provides you a way of getting labels on your data. Right? So it's looking for clusters. You have to pick the number of clusters, but once you've done that, it provides you with labels on those, so it belongs to cluster 1 versus cluster 2. Then you could do things like use those as training sets to do classification and regression. Okay? And in fact, ultimately what this allows us to do is the very important thing of drawing this line right here. This line here is essentially going to be like my regression line, because it's giving me a mathematical formula for distinguishing between one type of data to another. Okay? That's ultimately a lot of the goal of data mining, is to first look for clusters and then provide these lines of separation between the data. Now this case is fairly easy, right? If we look at this case, everything separates nicely. Let's take a more sophisticated case and see what that would give us. So I'm going to erase this data. It's probably a faster way than I'm going to do it, but fine. I'm going to just erase all this. Okay? And we're going to come up with a new data set. And the new data set is not going to be as clean as that one where I had everything separated. In fact, let me erase this line here that we have, our classification line. So in this case that I drew, and of course, oftentimes in textbooks, you always see these nice cases where everything separates out nicely and there's no problem and it's almost through the naked eye. You can make these distinctions about what they are. But in a lot of cases, it's a little bit more complicated than that. So let's go ahead and draw some of these orange circles. And let's just say that's my data. All right? And then I can say, well, what if I had another type of data? And then I could ask, do you think you have a shot at having a nice regression line that would separate the orange from the green, right? And that's a lot of times when you get data where the data analysis tricks don't work so well. But sometimes it's all about how do I get this down into that representation in the first place? And this is where something like principal components plays a big role, is in this sort of projection space of where I've put my data, is there maybe a more clever way to represent the data where it does separate out versus something like this, where clearly there's no way if I gave you a new set of data, let's say right here, and I ask you, what is that? You would not be able to say with any kind of accuracy that this was an orange ball or a green square, because in fact it sits there in a sea of orange and green. So these are the kind of ambiguous types of things where your clustering isn't going to give you a good separation. Even if you label these data, it's clear it's not going to give you a good separation. So in the data analysis here, there are serious, let's say, drawbacks that you might encounter with such type of data. Okay? So but this can represent realistic data that you would have in practice, and so it's important to understand that a lot of times you're going to see things like this. Okay? So we've given you one case where it's a nice separation, one case where it's not a nice separation. Let's do what's more typical, which is kind of some hybrid in between where you get some separation, but you get some mixing. And so let's go ahead and I'm going to show you one example of that. And I always think of this as sort of being, this is kind of what you more get in practice than anything else. All right, got all that erased. And let's go put some more dots down. Okay, we're going to go back to green squares. So I might have some things out here. Nice cluster of green squares. All right, and then I might have my orange data as well. There's the orange, and okay, let's look at this example here for a moment. So now in this case, you clearly see that most of the greens are below, most of the red oranges are above. So there is this nice separation. So if you were to do some kind of clustering analysis and you didn't know the number of clusters, but if you did manage to pick two clusters, what you would find is probably something bunched up there in the orange, something bunched down on the bottom in the green. Or even if you were to do a supervised, which is if you labeled these things, you would see this thing and say, here's a bunch of orange balls, green squares, and what I want to do is these two things here at the end of the day, classify, regress. In other words, figure out how do I want to classify new data and how do I draw a regression line, which ultimately leads me to a way to separate the data. In this case here, you might think that the best separation line, I don't know, let's just draw something, might be something like this. So again, anything above here is an orange ball. Anything below here is a green square. So in this scenario, you get a nice separation, but notice you're going to make mistakes. And by the way, that's the general thing. What you hope to do in data analysis, even looking for data mining and patterns in your data, is that what you hope to do is get the right trends, maybe even get accuracies in the 80s, 90s percents, right? That would be fantastic. Even if you can sometimes get above coin flip, it's pretty good. So if you can do better than just guessing 50%, maybe you find your accuracy is only 55%, but that's still better than just a pure guess. But something like this, clearly, you already see. Right here, I have this green square, and that green square gets misclassified. In this algorithm, it would say that this green square is actually an orange circle, and that's wrong. So you've made a mistake. However, you got most of the other ones right. Now, on this side over here, you get a lot of the green, but look at this guy right here. That gets misclassified as well. So this one here gets misclassified as a green square. So you've made a mistake on this side, you've made a mistake on this side. And also things like this one here, which sits right on that boundary line, it doesn't know quite what to do. Basically the algorithms has double precision accuracy. So at some level of 10 to the minus 16th, it's going to be on one side of the line or the other, and it's just going to simply get classified as being one of these or one of these, okay? But these points are very interesting because they're right at the border of your decision space. On one side, you're going to get one way. On the other side, you're going to get another way. So that's a kind of a more generic thing. You're going to make mistakes. You're not going to get perfect classification. Now, the one thing I'm going to highlight here is that I think one of the biggest dangers in data analysis is this danger of overfitting your data. And this can happen a lot in the supervised learning algorithms. You have to be really careful. And we're going to talk about this concept of cross-validation. I'm going to illustrate it here. If I wanted to do some kind of classification on this data, and this is my training data, and I want to do a perfect classification task, I might draw something like this. Let me see if I can do it here. Go around here. And I could say, hey, look at that. If that is my decision line, my classification, I'm going to get everything perfectly right. The problem with something like this is I can take any training data, and if I want to generate some sufficiently complicated curve, I'll get 100% accuracy. So it's going to start talking about the idea of cross-validation, which is how well does this hold up when I put new data to it? Okay? So the idea of cross-validation is extremely important. Perhaps maybe the most important thing to take out of all of this is you better cross-validate. How would a cross-validation procedure work? And by the way, always. All right? Always you cross-validate. Never miss doing this step. Okay? Never, ever miss doing this step. If there's anything you want to write down here, always cross-validate. So how do we think about it? Well, cross-validation says the following. How about I do this? Since I'm going to provide labels to data, and this is going to be my training set, what I'm going to do is take all my data that I have. Suppose I have 100 orange balls and 100 green squares. Suppose I had that. Well, one thing I could certainly do is take 80 out of the 100, randomly chosen. I'm going to take 80 randomly chosen here, 80 of the 100 randomly chosen here. So, I'm going to take 80%, and I'm going to have that be my training set. So I'm not going to train with all the data I have. I'm going to train with 80% of it. But what I'm going to do now to go test new data is I'm going to hold the 20% I withheld is going to be my test data. Okay? So I take 80%, I test with 20%. And I'm going to draw a decision line for every time I do this. So I'm going to test it, and I'm going to get an accuracy. So I'm going to get some kind of accuracy score. But then, once I get an accuracy score, let's suppose I do this, and I get some decision line, and I get an accuracy of 95%. What I'm going to do is maybe I just got lucky. Maybe when I didn't pick this problematic guy here, and this problematic guy over here. So I'm going to shuffle. I'm going to take a new 80% and test on that remaining 20%. And I'm going to do this randomly again. Take a new random 80%, test on the other 20%. A new random 80%, test on the other 20%. And what I'm going to do is keep track of my accuracy as a function of these random trials. And what ends up happening is you no longer get curves like this. This curve was very specific to this exact data pool. If I take another random sampling of it, this curve will be a bad predictor. Typically, that's how you do cross-validation. You would actually start evaluating for every decision curve you make, how accurate is it, and how robust is it if I take a new set of training and test data. Okay? So this cross-validation step is absolutely critical. Never present your results on data unless you've done this. Ever. Okay? It's really, really important. You're just being lazy if you don't do it, and nobody will believe you if you don't cross-validate anyway. Okay? So those are the highlight ideas. Unsupervised learning, look for clusters in data. Supervised learning is once I have labels or clusters in my data, that's what I'm hoping for, provide some kind of classification or regression on that. In other words, draw those decision curves. And whatever you do in this process, whatever classification or regression curve you get, always cross-validate. Always check to see what kind of accuracy do you get if you do a random trial and you shuffle. Okay? So those are the major highlight concepts that we want to test in pieces of code that we have next. And so there's that snapshot, and I'm going to present in the rest of this lecture two methods. One is kind of essentially the bread and butter unsupervised learning algorithm. It's called k-means. And in the supervised learning, I'll present one of the simplest ones, which is called k-nearest neighbors. And they're very intuitive, and we're going to write some code to go through it, and we'll start with that next.